Hi guys, my name is Sharan, and my teammates are Jivit and Krutik. We are from team 32. So our project is Kannada detection model. So when we go to the motivation, the reason what motivated us was like we are from Karnataka in India, where we speak Kannada, and we wanted to promote and preserve our language internationally. So what we thought was if we do some cool projects around this, there would be some digital footprints of the language and data available online, which can be later used for our next generation. So if you go to the problem statement, it's we wanted to develop a machine learning model which it accurately identifies and classifies Kannada numericals. So the screenshot what we have attached below, it represents how the digits look like in Kannada language. So the implementation method that we thought was we wanted to use a pre-trained ResNet 18 model. So that would serve as a baseline model, and then we wanted to build a custom CNN with better accuracy. So if you look onto the data set, one important point what I would like to bring here is first we thought of we'll contact some Kannada scholars. We'll ask them to write these digits and uh, the, the digits and data on a paper and send us that, and then we'll be pre-processing that data, creating an image data set, and then doing our model stuff. But luckily we found out there was someone who had already done this step, so it saved us a lot of time and we were able to use their data set, which contained around 60,000 images uh, for each digit. So like if you see on the x-axis it's like 0 to 9, which represents each digit, and we are able to get a uniform classified distributed data set. So this is how the data images looked like. They were grayscale images of handwritten digits. So if I just go here, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this was the data size that we had. Okay, coming to the important part of our model. So we used a pre-trained ResNet 18 model with which had ImageNet weights. So we are leveraging the transfer learning of ResNet 18 model, which was pre-trained on this ImageNet data set. This approach was beneficial as it used weights that were already tuned to recognize a wide range of features and which could be later fine-tuned for specific tasks. ImageNet is a large visual database which is designed for visual object recognition and research. So if you see the training and test validation split, the majority of our data, 90%, is used to train the model, ensuring it has large enough variety of examples to learn from. And validation results are 10%, which are the remaining data. This was for to evaluate the model's performance on the data it hasn't been seen during the training. For optimizer, we use stochastic gradient descent, which is a popular model, which is very popular, and it updates the model's weights based on the gradient of the loss function. For loss function, we use cross entropy loss. This is commonly used for classification problems. It measures the performance of a classification model whose output is a probability value between 0 and 1. So these are the baseline results. We are able to run it for 10 epochs. These are the training loss and validation loss, and we're able to see that it was detecting the images properly. And then in our final model, we built a custom CNN model, which was very lightweight. This was the main benefit that we achieved. And the second thing was we were able to bring better accuracy. So these are the two main important improvements that we are able to bring from our baseline to our final model. So these are the results of our final model. Even it was able to detect everything properly. So this was training loss and validation loss for 10 epochs. Here's the comparison of the results. This was for our baseline model and this is for our final model. Thank you. This was our project.